So in this technical talk, I want to share with you some of the most recent work in the area of computer vision. And the title really speaks of what I truly believe. Vision is not just about imaging. Vision is an integral part of the deepest intelligence that nature has given us for the past hundreds of millions of years, which is understanding. Well, the topic of intelligence started since the dawn of human civilization, and we have philosophers like Descartes asking us who we are and how do we define ourselves, and the very essence of being human and probably being intelligent is the fact that we can think. Well, fast forward hundreds and thousands of times, humanity is at the time that we are daring to think about making thinking machines. And this is the field and the blossoming field of artificial intelligence. When it comes to the field of AI and the daring thought of we can make machines think, we have to really pay tribute to one man who is Alan Turing, way ahead of his time. He was a mathematician during World War II. He was already pondering about what it means that we can build machines that can think. And here is an important quote coming from Alan Turing, that to build an intelligent machine, it may be best to provide the machine the best sense organs that money can buy, and then teach it to understand and speak English. So if we were to unwrap what Turing really think intelligence entail, I think there are two important components we should pay attention to. One is the sensory component. In Turing's words, he used sense organ. Humans, as an intelligent animal, has multiple sense organs. We have hearing, we have smell, we have touch. Vision is the largest sense organ in human being. More than 50% of our cortical functions are involved in vision, and it's one of the oldest sensory organs. So vision is very much a centerpiece to this sensing component. But vision is not complete unless we have understanding, and this is what Turing is getting at. The key part of the human level intelligence that we're going after is understanding. And it's really hard to define understanding. A lot of understanding is implicit, intuitive, and we just know. For example, I have two kids, and my daughter is only 1 year old. She doesn't really talk, but I do know she understands. She makes sure she cries louder when I put her in the bed to sleep, and she knows that I feel uncomfortable seeing her cry. So understanding is very nuanced, but there is an important part of human understanding that's unique to us, that is language. So for the rest of the talk today, I'm gonna just loosely interchange the term understanding and language, even though I do recognize understanding is more than language. So Turing says that intelligent machines needs to sense and needs to understand. So how does that influence the field of computer vision? When it comes to enabling machines to see and understand and connecting that to language and labeling, the first task that has been really important for the field to conquer is object recognition. Objects are the building blocks of our visual world, and thousands of papers and years of research and efforts have been spent in object recognition. For those of you who are in the field of computer vision, you probably know we have gone through several eras. We started with the era of very little data in Caltech 101, and such data sets started to boot the research of object recognition. And then an important data set called Pascal was has really helped the field to gel together the concept or the machine learning tools with the problem of object recognition. And then not long ago, a Stanford effort called ImageNet became one of the most important driving force of object recognition. And if you look at the collective progress of object recognition using ImageNet as a benchmark, we have very good news to report. The y-axis is the error rate. We want to see it as small as possible. And the x-axis shows the progress of ImageNet challenge since its inception 2010. And we are seeing a dramatically steady decrease of the error rate to the point by 2015, 2016, the machine error rate for ImageNet classification is on par with human error rate. Granted, this human is represented by one single Stanford graduate student on behalf of humanity. So, but I think we have good students. So while I don't claim the entire problem of object recognition is completely solved, because we still have a lot of work to do in terms of parsing objects into parts, the 3D modeling of objects, or object recognition under extreme conditions like moving mobile phones and so on. But in general, we have made tremendous progress in object recognition. It's one of the biggest success stories of computer vision in the past 20 years. So moving forward, recently the field of computer vision is pushing Turing's dream further and starting to look at what's beyond object recognition. What else can we say about an image that shows our machines can understand more than just giving it a single label, cat or couch? Well, that's the question of image captioning. Again, image captioning is kind of an old topic. When I say old in computer vision, it's about 20 years. And a lot of people in the past have made a lot of efforts in this. But recently, image captioning made a huge progress because of deep learning, because of the more powerful way of representing images using convolutional neural network, as well as representing language using recurrent neural network. This is a work that my students and I did around 2015, 2016, where we show the computer one image, and the computer is able to output a sentence that is human-like in order to capture the overarching story of the picture. Around that time, multiple labs around the world has made similar effort, and truly 2015 marks the first year that that machines are capable of speaking a human-like sentence when seeing a picture. And here is a result. This is an automatically generated caption by our deep learning algorithm. Upon seeing this picture, the computer says a construction worker in orange vest is working on a road. And here's another example. A man in black shirt is playing guitar. So quite impressive result. I am personally pleasantly surprised how far we have gone from letting computers to give one label to an image, cat, chair, dog, to giving a sentence to an image. So what is next? What is beyond? Clearly, we haven't fully realized Turing's dream, not even to this day, but a lot more progress needs to be made in order to enable computers to see and understand. So already we have seen giving one label, which is a main object label to a picture, and that's what ImageNet does. And then the image captioning work, driven by data sets like COCO, start to give a summary sentence and a few more objects about this scene. But there is a lot more that is going on. There's a lot more that is going on in this image, such as multiple stories and multiple center of interest, as well as you can ask questions or understand relationships. In fact, all the entities and relationships in the scene can be made into a scene graph that can represent the visual world not only by objects, but also by interactions and attributes. And this is an ongoing effort as a collaboration with Professor Michael Bernstein at Stanford. It's called the Visual Genome Dataset. I won't be able to get into the details of Visual Genome Dataset, but the idea is that we're going beyond labeling objects. We're even going beyond just a simple sentence summarizing what this image is about. We're going into relationships, attributes, multiple stories, and the deep interconnected understanding of what the image world is. And for having assembled the first version of the Visual Genome Dataset, we are working on multiple projects that are related to a deeper understanding of the visual world. The first project is relationship prediction. Again, we're going beyond single objects. So if I have two images and I tell you both have two objects, llama and person, they don't, just that description alone doesn't tell you what these two images is about. It sounds like they're the same image. But it's the relationship that mattered. Seeing what the inter-object relationship is defines the story of the image. So this is what we wanted to do here. We want to give a picture and then be able to label all the objects and the inter-object relationship. And of course, there's been a lot of related work, but mostly limited to small scale and closed world labels. I'm not going to get into the deep learning model that we put together, which has both a visual module as well as a language module. I'll just skip through this. But here's some result. If I give you this picture, our algorithm is capable of labeling relationships and objects such as spatial relationships, comparative relationships, asymmetrical relationships, verb relationships, and prepositional relationships. So together, this is a much more complete understanding of the scene. And here are some numbers that shows we're good. And beyond that, we can even do zero-shot detection. For example, we've learned person can sit on the chair. We've learned fire hydrant is on the ground. Our algorithm is capable of doing a zero-shot prediction of person sitting on fire hydrant without any example, training example. Here's another example of horse wearing hat. Again, no training example, but learned from the previous people wearing hat and people riding a horse. And another project that's ongoing is image retrieval. This sounds like something that we already have products for, right? Like if you go to Google search, you get nice returns when you will query for images. But try query man wearing suit holding cute dog. When you try to query a sentence, Google image search results are actually pretty bad because there isn't enough understanding. So what is the problem? The problem is objects, as well as just object attributes alone, don't give you the full story that the rich visual world is about. We need relationships in order to complete this, the full understanding of the scene. And here's another example. So our hypothesis is that instead of querying with discrete objects, we query with scene graphs. Once we turn a sentence or image into scene graph, we can retrieve results a lot more accurate than just single object-based labeling. And here's another example. So we got very good results querying using scene graph. And, but here's one caveat, is that it's really exhaustive by hand to make the scene graph. And that's what we did in our first work. We have to have students making scene graphs by hand. In the recent submission, we have automated this process where we have built a deep learning algorithm that can make scene graphs automatically given an image. Let me just skip through the results and show you another last work is not only now we can do relationship prediction and image retrieval, we can also do dense captioning and taking an image. Now we can look at different regions of the image and be able to speak sentences, not just one sentence per image, but multiple sentences to describe the fuller story of the scene. And here are a couple of results. And recently, we have taken this even a step further and enabled a new model to be able to speak in paragraphs, which are not just concatenation of sentences, but a clever combination of different parts of the scene into a coherent human-like paragraph. So I see that Steve is standing next. So let me just rush. I was going to show you a video work, but I'm just going to skip that. And rush to the very last part that I just want to say, well, as you can see, we have been putting more and more efforts in enabling computer models to not only just see a few objects, but truly towards understanding a scene or understanding the visual world. Where do I think our next step is? I think our next step is really reasoning, not just understanding, but be able to reason. And here, offline, I'll share with you more work by a pioneer at Stanford, who is Professor Terry Winograd, who has, in his early days of AI research, done some phenomenal seminal work in terms of doing reasoning of a scene. For example, you know, the reason about not only the relationship, but causal effects of object interactions. And this is where I think the next step for computer vision is and for AI is. And I'm happy to share more with you about this offline. Thank you.
Thank you. Thank you, Fei-Fei. Fei-Fei, should we try to take maybe a moment for one question while our next speaker connects their laptop? Chris, can we ask you to come up and we'll multitask here? And is this work? Yes, this is now working. Here, you can use this. Do we have one question for Fei-Fei? And I believe we have microphones roaming the hall for questions. Anyone? Yes, we do have one question.
You've done a lot of work on analyzing images, you know, understanding relationships, but usually when you move around the world, you're dealing with moving things. And a lot of other people are doing work on sort of predicting things by looking at images, what would be the next scene, which is a little more subtle. I was wondering if you had any comments on that.
Yes, of course. So videos are very important. It's innate to human perception. And by last year, 2016, 70% of the internet data is in the form of videos. So the short answer to your question is, if Steve were to give me 5 more minutes, I would have shown you my video work. But a better answer is later today, you'll hear from my colleague, Professor Juan Carlos Niebles. He will be specifically talking about video research at Stanford.
Great. Thank you very much, Fei-Fei.